so it's a joint work with Marc Bonamy, Nicolas Bousquet, Pierre Charby, and Stéphane Thomasé. So we'll be considering the following primes, or should I have checked maybe? Does anyone know how to switch to? Okay, so now if I go. Okay, so we'll be considering the following primes. So we have a bunch of disks in the plane or in higher dimension, and we want to find a maximum collection of disks which pairwise intersect. So a possible solution could be like this. And we'll also consider the scenario where we're just given the abstract graph representing the intersections between the disk, and we would just want to solve maximum clique on this graph. So there is a very elegant algorithm for unit disks in a plane. You can solve max clique in polynomial time. So it goes like this. You guess two centers which are farthest away in a solution. And then you remove all the centers that would contradict this maximality. And you show that this diagon, this shape in bold here, actually induces the complement of a bipartite graph. So now if you solve the complement problem, maximum independent set, well, you can do it in polynomial time, and it solves your initial prime. So for these graphs, now when the radii can be arbitrary, maximum clique, the complexity of maximum clique is not known. So for basically all the other optimization problems, they are NP complete because they all already are on planar graphs, but of course this doesn't tell us much for the prime clique. And despite this, the question is open, there was some approximation design. So there is a 2 approximation for these graphs and a 2.56 for unit balls. And the prime was only known to be hard when the dimension is grows with the input, so when the dimension is logarithmic in the input. So with Giannopoulos, Kim, Janjeski, and Sikora, we showed that in a previous paper, we showed that for these graphs, if you look at complements of these graphs, this structure cannot, this type of structure cannot happen as an induced subgraph. And this structure is 2 odd cycles that are independent, so they are induced and they are not linked by any edges. So let's rephrase, or let's define this induced odd cycle packing number as the maximum number of odd cycle that you can pack in an induced fashion. So in a way that there are no transversal edges. So we showed basically that complement of these graphs, they have IOCP smaller than 1. So now you can ask, does it help? Now can we solve maximum independent set, the complement problem, faster on graphs which do not have this type of structure? And we also showed that yes, and we got a quasi-polynomial time approximation scheme and a sub-exponential algorithm for those graphs, which implies the same algorithm for maximum clique on these graphs. Now, first question that we tackled in the Fox paper, what was maybe this obstruction for these graphs also holds for unit ball graphs. So let's try to see how we can represent the complement of an odd cycle with unit balls, so in dimension 3. So okay, we have this cycle V1 to Vs, and it will be represented by points in R3 from X1 to Xs. And well, X1 and X2 are non-adjacent, right? So if you try to represent the complement of an odd cycle, I will play the following game. So I will move continuously a vector in the following way. So I start with the vector at X1, X2. Then I move continuously X1 to X3 along the segment X1, X3. So I will reach this state. Then I fix X3 and I move X2. So I move X2 to X4. And I continue like this. So basically, when I'm at I plus 1, I goes from I to I plus 2. So I continue. And this is the only place where the parity intervenes. Because S is odd, we'll end up with the vector in the opposite direction. Okay, so I will continue and reach the initial state. So now, if you forget about the norm of this vector, but care just about the direction, and look what the directions are drawing on a sphere, well, you draw something which is a closed curve, which is antipodal. So if you go to a place on the sphere, you go also to its antipode at some point. Okay, so we don't want to represent just one odd cycle, we want two odd cycles with full adjacencies between them. So they will both draw some antipodal curves on the sphere, and two antipodal curves, they necessarily intersect, meaning that they will share a common direction. So let's say that this common direction is the direction xi(x), which is also the direction of yjy. So you see that so one cycle is in blue, the other in red. So for the cycle in blue, xi was fixed, and we were going from xi minus 1 to xi plus 1. And for the red, the same thing with yj fixed. Now at this, with those 4 points, xi, yj, xy, they are coplanar. So in particular, the sum of the diagonal is larger than the sum of opposite sides. And we can focus on the left case. The two cases look similar, but they are not symmetric. So we need to deal with them separately, but just focus on the left case. We'll reach a contradiction to this first inequality because, so we know that the distance between yj and xi minus 1 or xi plus 1 should be less than 2 because there is an edge between the corresponding vertices, while the distance between xi and xi minus 1 or plus 1 should be greater than 2 because it's a non-edge. So, okay, we get that the distance between yj, well, let's rephrase it this way. So if you look at xi plus 1, it's closer to yj than it is to xi. So in particular, every point in the segment xi minus 1, xi plus 1 is closer to yj than xi. So x is closer to yj than it is to xi. And symmetrically, the distance between xi and y, so the other diagonal, you can also show that it's smaller than the red opposite side. So then we get the contradiction here. So, okay, we got the same obstruction for unit balls than we got for these graphs. Now let's see if we can improve, well, we have a QPTAS and a sub-exponential algorithm. Let's try to improve this QPTAS to an EPTAS. So we'll design an EPTAS for maximum independent set on graphs with constant VC dimension and constant induced odd cycle packing number. So the VC dimension is of a set system is the maximum size of a set with all possible intersections with the set system. And what I call VC dimension of the graph is just the VC dimension of the set system induced by the neighborhoods. And alpha of G is the size of maximum independent set. So we have the following approximation scheme for maximum independent set. So it's E efficient because you see that the exponent in n does not depend on epsilon. And we have actually not 2 assumptions, but 3. So constant VC dimension. This induced odd cycle packing number should be small. Here we will show with 1, but it works with any constant. And also alpha should be fairly large. It should be linear in the number of vertices. So for these graphs and unit ball graphs, the first condition is known to hold. VC dimension is bounded by a small constant. For the second condition, we can Turing reduce to instances with this property, so let's take it also for free. And we showed the third bullet just on the last slide. So now we can just forget about this graph and mutable graphs and concentrate on these statements just about graphs. And to sketch the algorithm, I just need the fundamental theorem from VC dimension theory by Osler and Wiesel that set systems with VC dimension D and only sets of size larger than an epsilon fraction of the total universe have small heating sets. So they have heating sets the VC dimension over epsilon log 1 over epsilon. And moreover, if you take a large constant times this, you get a heating set with high probability. So just to anticipate on the next slide, we will use this on neighborhoods intersecting with the solution. And maybe it's clearer if I draw a picture. So, okay, we want to solve maximum independent set. We can assume that the solution is linear, so it is large. So of course we don't know I, but we will sample, we will take uniformly at random function of epsilon vertices. And because I is large, with positive probability, depending just on epsilon, we'll land on I. So let's focus on the branch where we're lucky and we actually land on I. So S we include it to the solution, and therefore we can remove n of S from the graph. It cannot be part of the solution. And now in the rest of the graph, we have the property due to the result on epsilon nets that every vertex has a small degree towards I, less than epsilon cubed times size of the solution. So we'll compute the shortest odd cycle in polynomial time in the rest of the graph. And if this shortest odd cycle is small, smaller than 1 over epsilon square, then the combined neighborhood of this cycle towards the solution is also small. So we can just remove it, and the rest of the graph is bipartite. Why? Because we're in a non-neighborhood of an odd cycle, so there cannot be another odd cycle there. So in that case, we win. Now I have to tell you what we do if the odd cycle is large. And it's more complicated, so let's draw another picture. So we'll look at the consecutive neighborhoods of this odd cycle. So those are the layers, so those are the columns. And the columns are refined into strata, which tells you basically your closest vertex on the cycle. So if you remove any layer, what's on your right is bipartite, because you're in the non-neighborhood of an odd cycle. So you can solve maximum independent set optimally. So you will just find the lightest of the first 1 over epsilon layers and remove it. Now you're basically almost in the same situation, except the number of layers is now bounded by 1 over epsilon, while the size of the cycle is much larger. It's 1 over epsilon square at least. And okay, this is not so easy to see here, but if you remove blocks of 1 over epsilon strata, the rest of the graph overall is also bipartite. So it uses the fact actually that this was the shortest odd cycle, and if you try to go to jump over this red object, you will create the shortest odd cycle. So, well, those red objects, we have 1 over epsilon disjoint copies of them. So we can again find take the lightest one, remove it, and the rest of the graph is bipartite, so we can solve maximum independent set optimally. So it gives a randomized EPTAS, and you can have also a deterministic PTAS that I won't present here. So you could ask if this works also for other shapes in the plane or in higher dimension. And the answer is no. So let's call two subdivisions, graph that you can obtain from any graph by subdividing each edge twice, and co-two subdivisions, complements of those graphs. It's almost folklore that maximum independent set on two subdivisions cannot have a scheme, even in slightly sub-exponential time under the ETH. So max clique on co-two subdivisions doesn't have such algorithms. And now we showed that for many intersection graphs of objects, they contain all the co-two subdivisions, so in particular they have this lower bound. So it goes for very simple objects like triangles, ellipses pretending to be unit disks, so they have arbitrarily small eccentricity and arbitrarily close together radii. Balls, if they are not units, so in dimension 3, even if their radii are between 1 and 1 plus epsilon. And also unit disk in dimension 4. And it gives also NP harness for this class, so we went from log n to actually 4 for the dimension. Yeah, so basically if you go slightly away from these graphs or unit ball graphs, all this collapses. Let me conclude with the obvious open question, which is still if max clique on these graphs and unit ball graphs is NP hard or polynomial time solvable. And some leads would be to see what's going on with maximum independent set for graphs with IOCP1. And even, actually, I don't know if this is known, if the odd cycle packing, so the non-induced, the real odd cycle packing number is 1, the complexity of maximum independent set, to my knowledge, it's also an open question. I thank you for your attention.